Hi, in this lecture, we will be learning about LIME. LIME is a very popular technique within explainable AI. So in this specific lecture, rather than looking at how we implement LIME using a Python code, we will be looking at what is the underlying concept behind the method of LIME, and also what is the mathematical framework and which was the original paper that was published, which proposed the LIME method for the first time. So we will go through all those aspects in this video. So this is the original LIME paper titled Why Should I Trust You? Explaining the predictions of any classifier. This was published on Archive. It has more than 17,000 citations now. Let's just open this paper to see. Just have a brief look at the paper. I don't want to go through the paper in so much detail, but I just want you to have a look at it. So this was the paper, and they described the mathematical framework which makes LIME almost like a model agnostic method. So it can be applied for pretty much any machine learning models for explanations. It can work for text-based data. It can work for image-based data or tabular data. So it's basically like a very good method that you can apply for pretty much any machine learning model. And the idea is that you want to explain a specific prediction made by the model, right? So that's the idea behind explainable AI. You are not trying to create a correlation between. So let's say you have a healthcare data set where you have the BMI, the weight, and let's say the blood glucose level, cholesterol level, etc. of bunch of patients, and you want to make a prediction whether they are healthy or unhealthy. So on an average, you can say how much BMI correlates with health, how much blood cholesterol level or glucose level correlates with health. You can make those predictions, but still it's not enough when you are making prediction for one particular patient. So let's say a patient of age 55 years came and your model made a prediction saying this patient is unhealthy. It is not enough that your model is 99% accurate and you made a prediction for this patient. You also want to explain to the patient which features of this particular patient ended up making their prediction as unhealthy. Whether it was BMI, if it was BMI, what percentage contribution did BMI make towards making this patient's prediction as unhealthy, right? So that is what is the idea behind explainable AI. You are not trying to make always global explanations, rather you are trying to make local explanations. And that is exactly what LIME also does. So let's go back to the lecture slides. So I really recommend all of you to have a look at this paper. It's a beautifully written paper. But I'll still walk you through the basics of how LIME works and what is LIME. So what is LIME? LIME is local interpretable model agnostic explanations. So let's look at each of these terms. What do we mean by local? As I mentioned in the previous example, we may have data points about so many different patients, but we are trying to explain the reason why model made a particular prediction for a very particular patient. So that instance or that the data corresponding to that particular patient, that is the locality, and we are looking at making an explanation in that local neighborhood. I'll show this in a graphical format so that you will be better able to understand what this means. And interpretable means a human should be able to interpret whatever the explanation of the local instance is. So if we are saying that this particular patient was classified as unhealthy for these reasons, those reasons should be interpretable for a human. And model agnostic because the LIME method is applicable for all kinds of machine learning models. It's not just applicable for convolutional neural networks or It's not just applicable for decision trees. It applies irrespective of what model you build. And explanations means whatever interpretation you want to have regarding why the machine learning model made a particular prediction, you want an explanation that helps with your interpretation. So this is what LIME is: local interpretable model agnostic explanations. So let's start with a simple example. In this 2D plot, the x-axis is body weight and y-axis is exercise duration. So let's imagine that this is data points corresponding to different patients. So each of these dots corresponds to different patients or different people. When the body weight is high and exercise duration is low or small, they are generally unhealthy. That's what these blue dots are showing. So all these unhealthy people have generally higher body weight and lower exercise duration. But if exercise duration is small, if you keep your body weight low, you are generally healthy. Or whether you are your body weight is high or low, if you do exercise for a longer duration, you are healthy, right? So this is basically the intuition of this model. Now, when we say model, what exactly is the model here? Let's have a look at that. The model is this particular boundary. So the global model that decides whether a patient is healthy or unhealthy is this. It's not a simple model. It's complex. It's not necessarily linear, right? Although I have drawn a line here, it can be wavy. It can be in different shapes. So this is a complex, in reality, this is a complex non-linear model. And all data points to this side, to generally the right bottom side of the model, is unhealthy and all other points are healthy. I mean, this is fine, but let me go back to the full screen. This is what the global model looks like. But let us have a look at a very specific example of a very specific set of patients. So let's look at the difference between global and local interpretability. Have a look at these two people. This person in pink is healthy. This blue person is unhealthy because they both exercise similar amount, but this person is slightly overweight in terms of body weight. So the global model, which is the boundary between the pink and the blue region, the global model classifies this person as unhealthy. So what is the feature that distinguishes between these two guys? Is it the exercise duration or is it the body weight? Because these two are features. When we look at it, the feature that distinguishes these two people are the body weight. So if this person has to come to the healthy category, he or she should, instead of increasing the exercise duration, they should decrease the body weight, because if you increase the exercise duration, you are still in the unhealthy category. So this is what we mean by local interpretability. Like we are making local, we are finding the features that are locally relevant for making this classification. Let's look at another example. In this case, you look at these two people. This blue person is unhealthy and pink person is healthy. And in this case, unlike the previous case, exercise duration is the feature that distinguishes these two people. So this blue person, even if they decrease the body weight, the category is not going to change. What they have to do is increase the exercise duration. So when you look at the global model, which is the boundary between these two regions, here the global model locally says that the feature that is sensitive here is the exercise duration. So this is what we mean by global and local interpretability. So globally, by looking at the model, we cannot say whether somebody should exercise more or somebody should reduce their body weight. That's very difficult to say because the model is like we have drawn this like a straight line, but in reality this will be wavy or curvy. So this will be like a complex non-linear model, and it's very difficult to make local predictions or rather local interpretations just by using the global model. We have to look at the model locally, right? So that's what we mean by local interpretability. And that is exactly what LIME is trying to do. So this data set was like a tabular data set, for example. So what we mean by tabular data set is, let's say you have a list of patients and some information about those patients, including body weight, exercise duration, body mass index, BMI, or gender, age, and blood cholesterol level, blood glucose level. All these things are like a data frame. Like you put those in tables, and in those tables, each row will correspond to one patient or one person. So this is like an example of tabular data. But when we come here, this is an example of text data where we want to make a classification, but look at locally what is important. So here I have a medical emergency, hence won't be able to attend the meeting today. Second one is, hi, may I get the information about your service? Clearly, we know that this is important text, and this is not as important as this. So if we were to make a binary classification, this belongs to the important category, and this should ideally belong to not so important category. And what are the features that helped us make this prediction locally? Maybe the features are these particular words: medical emergency, won't attend meeting. So meeting is an important thing. Medical emergency is important. Not attending is also important. So maybe these are the 4 words among this sentence, or 4 features in this particular data point that contributed maximum to making the decision that this was an important sentence. Whereas here, information of service is something where it's not important to respond. So let's say you're building a AI agent, or you're building a system where you want fast response to queries, and this is a more important query. So to determine which query or which sentence is more important or something that should be urgently attended to, this is the way in which you locally use the local features to make a local prediction. So this is an example from text classification. And this is another classic example, which was also mentioned in the original LIME paper. Why should we trust your model? So in this example, what's happening is the husky. This is actually husky getting classified as a wolf. So in this image, the machine learning model was saying that this was a wolf. So, but that is fine because overall the model was still good. When it was trying to classify thousands of husky images or thousands of wolf images, it was making mistake only in a few cases. But does that mean that the model is an actually good model? So does, a percentage accuracy score, let's say the model is 99% accurate and it's only making a few mistakes. Does it necessarily mean that it's the right model, or it's a good model, or a trustable model? This is a classic example showing that is not the case. So here, husky is being classified as wolf, and such mistakes are okay. In AI, of course, AI systems will make mistake, but the problem in this particular case is that the AI is seeing the snow. So it's actually not looking at these pixels which are grayed out. So husky is this, not this. But if we can, plot using LIME method, we'll come to the details of how LIME does these. But ultimately, when we plot the pixels that prominently contribute to, helping with making a decision whether this is a husky or wolf, these are the pixels, and these are pixels that represent snow. So actually, this particular machine learning model is not a husky versus wolf classifier. It's actually a good snow detector. So although the purpose of someone who built this model was to predict between husky and wolf, they have inadvertently ended up building a snow detecting model. So it cannot be really trusted for classifying between husky and wolf. So that's the point here. So this is how explainable AI, or in particular LIME, works for images. And now let's look at this example where we are trying to explain image classification prediction. So in this case, Google's Inception neural network labels this particular images. The top 3 classes that the network labels are electric guitar, acoustic guitar, and Labrador. So electric guitar with a probability of 0.32, acoustic guitar with a 0.24 and Labrador with 0.21. And when we plot, so look at these three, B, C, and D, these three images, you can see that when we are trying to show electric guitar, it is actually showing the string area of the guitar. So in electric guitars, also the strings will be there, probably this region, which is meant for the acoustic. I don't know what is this called. I think this is called acoustic chamber or something like that. But basically this region can differ between acoustic and electric guitar, but the strings will be there. So it's rightly identifying the electric guitar strings. Whereas for acoustic guitar, it is detecting this this part of the main body of the guitar. And when the model is classifying as Labrador, it is looking at the right regions, mainly the face of the dog. I don't know why this part came. This is more like a t-shirt, maybe because I don't know if there's a leg or something here of the dog. I'm not sure, but more or less the model is looking at the right thing here, you can say. So this is exactly how you can say that the model can be trusted, provided the model also should have a good accuracy of prediction. So if you are trying to make a, let's say, dog versus cat classification for these images, of course, the model should predict that this is dog with a very high percentage accuracy. And for thousands of these images, the model should make good predictions with good accuracy. So then the model is good. And in this case, model can also be trusted. All right. So now let's look at the LIME in a bit more detail, how it works and the math behind the LIME. So the basic intuition that is used for building this LIME model is that unlike the global model, like unlike a big convolutional neural network model or unlike a big machine learning model which makes all the predictions, linear models are readily interpretable. So what does that mean? Look at this equation, y equal to w1x1, w2x2, w3x3. And if x1, x2, x3 are features, so if we go back to the this example, here there are two features, body weight and exercise duration. In this case, if we, let's say, ignore the w3x3, the y equal to w1x1 plus w2x2, and if x1 and x2 are the features, the weights w1 and w2 will tell you which feature among x1 and x2 is the most prominent. So if w1 is very high, that means sensitivity of y towards x, which is dy by dx1, will be very high. So dy by dx1 is w1, dy by dx2 is w2, and dy by dx3 is w3. So even if x1 changes slightly, y will change significantly because the weight w1 is very high. So that means that the feature x1 has more prominence. So if we can locally build a linear model, I'll come to that in a moment. Please don't be worried if you don't understand what this means yet. But let's say, hypothetically, if the global model can be represented locally as a linear model, then it has high interpretability. And what do we mean by high interpretability? Then we know locally what features are more dominant or more relevant. How do we know that? We know that from the weights. So if these weights or W1, W2, if one of them is much higher than the other, then we know that locally for that particular region, this particular feature is more relevant. So if we go back to this example, locally here, body weight is the more relevant feature, but locally here, exercise duration is the more relevant feature, right? Okay. So now how do we implement LIME? How do we build this local linear model? And what do we really mean by that? So let's look at the LIME. LIME is implemented in 4 different steps. So let's look at another sample data. So here we have x-axis and y-axis. Just ignore what are the features here. Just assume that there are 2 features. There could be multiple features, but just ignore that all for a moment. So this complex curve is the global model in this case. Anything below that, anything in this blue region are people with no diabetes, and anything above that are people who are represented by this yellow dots are people with diabetes. So this pink point is also actually another point belonging to the diabetes class, but I have noted it pink because this is the point that we are currently interested in. We want to know why this particular person, this pink data point, was predicted as a person with diabetes, right? So how do we, or why are we asking this question? Because from the global model, we cannot say that if the y-axis feature value is greater than, let's say, 0.5 or whatever, we cannot make a global statement saying, oh, if y-axis feature is greater than 0.5, then diabetes, yes, otherwise there is no diabetes. We cannot say that, because let's say the same point was belonging here. The value on the y-axis is still the same, but because the x-axis feature value has changed, this person who has diabetes will not have diabetes over here, right? So the global model is not sufficient to explain why this particular person was predicted to have diabetes or no diabetes. So how can we interpret the prediction made by the global model? So again, just take a pause for a moment. Don't worry if you are not fully able to picture the global model, or you're not fully able to picture why, the meaning of how the global model cannot be interpreted locally. So what I mean by that is, in this particular case, we oversimplified everything and we were able to plot something in 2D like this, right? But in reality, there are much more number of features. There are n number of features. So you have an n dimensional space, and you cannot really draw things like this. So it's very hard to visualize anything. So even if in this particular case, you probably can say that, maybe the y-axis feature is more relevant, because if this point moves a bit in the bottom direction, in the y direction, the person changes from diabetes to no diabetes. So in this particular example, maybe it's easier to interpret the global model. But in reality, that's not the case. In reality, these global models are much, much more complex. They are not even 3D. They are, you have a much more larger dimensional space in which you have the global model. And this model makes let's say it's a binary classification. It bifurcates the data points into two, class 1 and class 2. But let's look at this local vicinity. Okay. So here, if we zoom in, what we do is this global model, it may have a complex shape. So look at this blue line. I hope you can see the blue line. I think you can see the blue line now. So this blue line is the part of the global model in the vicinity of this pink point, right? So you have the pink point, there is a yellow point, which is diabetes, and blue point, who is a healthy person, no diabetes. And what we do is, we approximate this complex non-linear model, which is the blue line, which is this part of the curve, by a linear line. Like, we do a linear approximation of the blue line. Now, don't worry about the math of this yet. We will come to that in the later part of the lecture. If you don't fully understand how this linear approximation is done, just don't worry about that yet, because first let's build the intuition about the line, and then let's get into the math. So the model is locally approximated as a linear model. All right. Then what happens is, we take this point, right? We take this point and we generate more data points by perturbing the data, this point. So what happens is, we generate, in this case, x1 and x2, we generate features. We change the value of the features to generate these points, these new yellow points with black outline. So these are all artificial data points. These are not actual data points. What are the actual data points? Actual data points are these yellow, pink, and blue points. Now, these new yellow points plus this black point are generated by perturbing this particular instance. So this data point is called an instance. We are looking at a local vicinity of an instance, and we are trying to generate a interpretation for why the global model predicted it as diabetes, That's the goal here. So we create these randomly generated data points, and in general, we are not too much worried about points that are far away from here. So this black point, for example, or even this one, which are far away from our instance, we don't worry about it too much, because we don't want to move away too far from here, because we are trying to make an interpretation for this. Now, before going into the step 4, pause for a moment and think, what is this going to tell us? What this is going to tell us is, if this dotted line is the linear model, and when we created these bunch of points, and let's say now what the linear model is saying is, the points which are on this side are diabetes, and points which are on this side are people with no diabetes, right? So you can say which feature is more prominent in this local region, whether the feature on y-axis or feature on x-axis is more prominent. So imagine that this was a vertical line. Then what it means is the sensitivity is very high in the horizontal direction, because even if this data point is slightly to the right side, the classification changes. So when you randomly generate a lot of points around the instance of interest, and when we classify those points into diabetes or no diabetes in this particular example, we can kind of get a sensitivity for which feature is more important locally, and that will help us interpret the global model. I am aware that at this point you may still fully not understand the local model yet, because we are oversimplifying everything. This probably still does not explain to you how interpretability works in images or some other data types. But that's okay. Don't worry if you don't fully understand things yet. Just understand this much. The linear model helps us put a weightage to the features. So if it will help us understand whether one feature is more prominent than the other in a local region. And at the end of it, when we plot, so we can generate plots like this using the method of lime, we will know. So here again, I'm adding more features. So here there are 5 features, although I have plotted only 2 features here. There were only 2 axes. But let's say you have 5 features, then you will know that maybe BMI is the thing that was more relevant for classifying this person as having diabetes, right? This is not a real picture. This may be the case. Like in reality, maybe BMI does not contribute to diabetes, but this is just to show an example. Maybe there is a correlation between BMI and diabetes, and the locally for a particular person, like this pink person, this BMI is the biggest contributor to predicting this person as a diabetic patient, more than age or heart disease or gender or cholesterol, right? So this is how we implement lime in a few different steps. So this is an actual lime plot being shown here. So if a particular person is predicted as having diabetes with 0.64 probability and not having diabetes with 36% probability, we can create a lime representation for this particular data point or for this particular patient and get an idea what features about this patient resulted in them having diabetes with a higher probability. So this is the plot from lime. Here you can see that glucose being less than 100 positively contributed towards no diabetes. So that's why this color is blue. So here no diabetes is blue. This orange plot is for diabetes. So if glucose is less than or equal to 100, it is a good thing for not having diabetes. If you have insulin greater than this much, it's also contributing a little bit, very little minute towards having no diabetes. And same goes for pregnancy. So, but it has very little effect. But here you can see the factors that positively contribute towards diabetes. Age greater than 40 is a good contributor towards diabetes. BMI greater than 32 is a good contributor towards diabetes. And so when we say contributor, we are not saying for all patients, for all data points, these are the factors that contributed to the diabetes. What we are saying is, according to Lyme, for this particular patient, so this is the data or prediction probability for one particular patient. For that particular patient, age contributed by 0.24, BMI contributed by 0.1, blood pressure contributed by 0.09, etc., skin thickness, etc., etc. So here you can see exactly which features contributed by how much towards diabetes. So have a look at here. Glucose, insulin, glucose value being low, insulin value being greater than 129, and pregnancies, the number of pregnancies, they contribute positively towards no diabetes, and age, BMI being high, and then the blood pressure above a certain range, skin thickness, diabetes pedigree, function, these 5 features contribute positively towards diabetes, and these numbers exactly show the contribution of each of those features towards the final prediction for this local data point. So this is how Lyme helps you interpret the prediction for a particular instance in a data set. Now let's see how Lyme works for tabular data. So we have tabular data, we have text data, and we also have image data. So text and image, I hope you already know. Image is like any random image which you want to classify. Text is paragraphs which you want to process or classify as important or not important. Tabular data is where you have features and corresponding values like this. You have glucose, age, BMI, etc. as a table. So for tabular data, if X1 and X2 are the features, and if this is the instance we want to explain, we create sample points around this instance. So these are perturbations. And then we project these created samples into the model and let the model make a prediction, right? So let me go back to the previous slide once again. So here we had the pink point as the instance. These were perturbed data points. And for these perturbations, we try to make the prediction, right? Now coming back to here X1 and X2 are the features, and f of X1, X2 is the global model, global complex nonlinear model, which you can see here. And maybe this nonlinear model, what it is saying is, if the value of f is above this, it is then diabetes. If it is below, it is no diabetes. I'm just giving an example. The model can predict anything. But let's say that's what this model is showing. So then what we do is, so this pink point, let's say this pink point is a diabetic patient. So this pink points, when you project it onto the model will say the value is greater than what this plane or this curve is showing. So it's a diabetic patient. So what you do is you create a linear fit for the model. So here a linear fit for a curved 2D model is like a plane. So for this local instance in the middle, this local instance, we create a linear fit and we project the points and we try to classify the points according to the local linear fit. And then we can know based on the slope of this plane. So let's say this plane is sloped heavily along the X2 axis. So let's say the plane is like this. Then we know that the sensitivity towards X2 is very high. Even if X2 changes slightly, the model changes its prediction. So let's look at as an example, look at this region of the curve. Here, if X1 changes, nothing happens, because in the direction of X1 there is nothing. Like the model shape is the same. Whereas here, if X2 changes, you suddenly go from the bottom part of the model to the top part. I hope you understand what I mean when I say bottom part to the top part. So the model is bifurcating the data points if this is a binary classification. So I'm oversimplifying things so that you can imagine. And let's say below the model is, if f of X1, X2 is below this, it's one class, and above this, it's another class. And you select this instance, you make a linear fit locally at the model. So this is like a tangent to this curve. And based on the linear fit, you classify the perturbed points as, one class or the other. And then you can interpret whether this particular person, the instance of interest, whether that person was classified as one class or the another, more based on the feature x1 or more based on the feature x2. So ultimately, that's what interpretability is, right? Feature x1 contributed most towards this prediction, or x2 contributed the most, or both contributed equally. So that's what we want to predict. Now, let us look at the same thing for a text-based data. How would we do this? So let's say this is interesting stuff. So this is the sentence that we want to explain. So first what we do is we tokenize the sentence. So let's say the tokenization is like this. We divide the sentence into a set of words. And the way we create perturbations, similar to this. So here we created perturbations by changing the value of x1 and x2. Here, we can't change the value because these are the only words. So what we do is we randomly remove words. So we remove this to create this is interesting stuff. Here we remove this is word. So we create this and we create this. So we create perturbed instances, and then we project the same onto the model, right? So these are the perturbed instances around the original instance, and then we create a local linear fit at the original instance. So this curve is the complex nonlinear model, and we take the original instance. This is the original instance, and at the original instance, wherever it is the belonging to the model, we create a local linear fit. So the linear fit is the plane, and based on the slope of this plane, we can say which word is more prominent, whether this is the more prominent word, is the more prominent word, or interesting or stuff, which is the more prominent word, or which are the more prominent words in this particular sentence, which leads to classification of this sentence as, let's say, hate speech or humor or something else. Let's say you want to do sentiment classification. This is how you do that. So you can interpret the features or words which contributed to classifying this sentence as one thing or another. So that's what we mean by using LIME for text data. And finally, LIME for image data. So let's say we want to classify this image of a frog, and we want to create an interpretation for why this particular image was classified into frog or something else. This is how you do that. So before I explain this, I want to show you another thing. I just want to show you how LIME is applied to images. So for tabular data, you saw that the individual features themselves are interpretable. So if BMI, body weight, glucose level, blood pressure, these are the features, they themselves are interpretable. You don't have to change anything. The problem with images is images are represented as kind of like tensors, right? If you are trying to classify an image using a convolutional neural network, you take the pixel values. So if it is an RGB, there is red. So this whole image will have, let's say this is 255, this is 300 by 300 pixel. You will have 300 by 300 red values, 300 by 300 green, and that many blue values. And then you convert all of this into a tensor. So that is a representation of an image which the convolutional neural network uses. But generating interpretability for that tensor is not useful for humans, because what is really useful for a human is to know what regions in this picture contributed to classifying this as a frog or like a heart or something else. So what we do is we subdivide the image into interpretable components. So these are the subdivisions, each of these individual islands. And what we can do is we randomly, so the perturbed instances now are these pixels where the rest of the pixels are grayed out. So these gray pixels do not contribute towards a classification. In this particular perturbed instance, only these pixels contribute. And we create a probability for this being a tree frog. So here it's 0.85, here is 0.0001, 0.52. And then when we take a weighted average of all of this, we can see that ultimately these are the pixels which contributed maximum for making this prediction of this image as a tree frog with 0.54 probability. So here basically we present the super pixel with highest possible weights. Those super pixels explain why the model predicted this frog image as a tree frog with 0.54 probability. That being said, the neural network or the model which is predicting the frog also predicts. So this model predicts the image as a frog with 0.54 probability, but it also predicts the same image as billiard balls at a 0.07 probability. So this is a non-negligible probability. It's very interesting. And if you really look at what are the pixels that really contributed to the model making the prediction of this image as billiard balls are these two, the eye of the frog and these two. So the fingers of the frog looks like a billiard ball, kind of, right? Like not exactly, but there is a non-negligible probability that the model also sees billiard balls due to these pixels. But due to these pixels, the model sees tree frog. And finally, due to these pixels, which belong to this heart, the model sees like an air balloon, hot air balloon. Because this is red, this is also red. So there is a 5% probability that the model sees, instead of a frog, it sees a hot air balloon. So this is how you can interpret what the model is seeing. But you can still see that the model is quite good. It is able to see frog with the highest probability. So this is what the neural network sees, and this is exactly how LIME allows you to. So these super pixel representation of image of what the neural network is seeing is generated using the technique of LIME. Now let me go back to the LIME for image data. So what we do is we segment the image into these segments, or rather super pixel. So we create perturbations. So we create new samples by turning on and off super pixels. So here, whichever are turned off are colored in gray. So we have this, we have this, we have this, and we have a bunch of similar images. And we feed that, or we project that into the model. And then we will see, and then we'll create a local linear fit. I am fully aware that in the case of images, it's very hard for you to visualize the shape of the model, the linear fit, etc. So which is why I don't want to you to imagine about this, but it's probably easy for you to imagine the model and everything in, if not in this case, you can easily imagine that in this case. So keep your imagination here so that it's easy for you to understand and believe the process of LIME. These slides, like even if you are not able to imagine the model in this particular case and the linear fit in this particular case, don't worry about that. It's completely fine. You don't have to know that, or you don't have to have an ability to visualize that. It's okay. But basically, at the end of the day, we have a collection of super pixels like this, which explain the model. So if the classification of the model is as tree frog, these are the pixels that does the maximum contribution. In this section, we will be looking at the mathematical details behind how LIME is implemented. So this is a little bit detailed section, and it's likely that you may find it a bit difficult. And it is not my intention to make, the mathematics behind LIME appear difficult for you. But the good thing is, for actually implementing the approach of LIME in real life, you don't necessarily have to know the underlying math, because there are GitHub repositories with the code for LIME already written. There are libraries which do these things for you. So when you actually implement LIME for images or tabular data or text, you will not be going through these mathematical steps. But the reason why it's good for you to know how LIME works is because then you may have a better intuition when things do not work for you when you implement LIME. So just patiently go through let's go through this the mathematical representation or mathematical implementation of the concept of LIME. So firstly, as we saw in the previous part, in LIME we are trying to predict or trying to interpret for the reason why the model made a certain prediction at a local instance, right? So let X be the local instance. And this local instance can be, let's say, if the local instance is a particular image of a frog, then the original representation of the instance which is used in the model is probably in the form of tensors. It's not in the form of an image. But we need to convert this representation into something that is something that is interpretable for humans. So X is transformed into X prime, where X prime is a human interpretable representation of the same instance. So if it's an image, the human interpretable version of the same thing is, if you remember the segmentation, images segmented into different islands. So those segments are something that are interpretable by humans. I don't want to go into every single detail of the symbolic representations here, but basically here H is the function which transforms X to X prime, and H inverse transforms from X to X prime, and X inverse is transformed to X using H. And the good thing is, if you have data in the form of tables like tabular data, you don't need to transform X into X prime. X itself is the X prime. Why is this? Because tables are already interpretable by humans. Like if you remember the patient data about BMI, about cholesterol level or blood glucose level or insulin level, whatever, like whenever you have a tabular data format, it's already interpretable, so no need to transform. All right. So now in Lime, what we are trying to optimize is this function. Do not worry. I know that the slide is a little bit crowded slide, but let's look at it one by one. We will not approach this equation from its complexity point of view, but let's look at it component by component. This zeta of X is the function that we are trying to optimize. I will come to the idea of optimization. I'll come to that in a bit. This zeta of X is the function. X is the instance which you want to explain, right? So you want to explain for this particular instance, maybe what are the features that were most relevant, right? And you have two separate functions here, L of f, g, pi, and omega. The function L depends on f, g, and pi. So what is f? F is the complex model that is being explained. So if you remember the curved complex model which explained diabetes versus no diabetes, F was that complex model. It's complex and non-linear, right? G is the simple linear model. It's also called as surrogate model. And this linear model, G, belongs to a family of interpretable models. So linear is one of the interpretable models. There could be other models as well, which are interpretable. So the complex function complex model F is being simplified into a simple linear or other family of interpretable models. And where are we doing this? We are doing this in the neighborhood of X. So what do we mean by that? Let me go back a few slides. So here, this is X. This is the neighborhood of X. We can define a particular, size of this neighborhood. And we are trying to, so here the G is the interpretable function, which is this line, straight line, not the blue curved line, the dotted straight line. And F is the complex nonlinear model, which is this. So I hope, so basically that math which you see is just a, representation of the concepts that we already discussed. So you already know what this math is talking about. It's just that the symbolic representation in math is a little bit intimidating, but don't worry about that. So neighborhood of X is pi, simple surrogate model, it's G. This is the linear model. Complex model is the nonlinear curve. And an example of X could be, if it's a tabular data, it could be one row. So if you have data about different people, let's say this person is a male of age 37 who exercises for 125 minutes, BMI is this much, weight is this much. So this is one data point, one row. So similarly, this row is an example data point within the data frame. And what we are really trying to optimize is this function. And in this function, we have two loss terms. First is this one, the L function, and second is omega. I did not mention what is omega yet. Omega is a measure of complexity of G. So G is the simple or surrogate model, right? The simple function using which we are locally approximating the complex function f. And we want it to be interpretable, or we want the function G to be simple enough for a human interpretation. So this omega function is a measure of complexity of G. You may not be able to imagine the mathematical representation of omega yet, and that is completely fine. You also may not be able to imagine the mathematical representation of the function L. That is also fine. But just understand that there are these two terms that we are trying to, these two loss terms using which we are trying to optimize this problem. All right, so I hope now this equation looks a little bit less intimidating for you. Initially, probably it was looking like a random set of Greek letters. So now let's look at the function L. One of our goals is to minimize this loss function L. And what we are trying to do, as I showed you earlier, is to know the local behavior of L in the vicinity of X. So X is this, and we are generating the perturbations pi X. Sorry, there is a font issue here, but basically we are generating perturbations pi X. So the perturbations are these points, these yellow dots with black outline. This is not a perturbation. This is an original point which was already there in the data. This is also an original point which was there in the data. This was also there in the data, but this black point is perturbation. These are all perturbated points. So we generate perturbations pi X within the vicinity of X. So vicinity we will define as per our convenience, right? So this function L is what we are trying to minimize. So what is the format, or what can the function look like? Let's imagine, right? So if we want to minimize the loss for the linear function, we are looking at how different or how far away this function is from the like how far away the linear model is from the original complex model, right? So let's say this dotted, let me go back to this slide. Let's say this dotted line was over here, right? So you see this blue curve. Blue curve is the complex nonlinear model. Dotted straight line is the simple linear model. Imagine that this simple linear model was over here, this line. Then there is a gap between the simple dotted linear function and the complex nonlinear blue curve, which means that simple linear model is actually not able to approximate the blue curve because it's not going through. It's not being like a least square fit through the blue curve. Of course, we are not doing a actual least square fit. It's a little bit more complex, but I hope you understand the idea. So, so you want to minimize the distance between the blue curve and the straight line according to certain constraints. So if you look at this function here, you are calculating not exactly the distance between those two lines, but at least, f of z minus g of c and the square of that. So this is like a measure of how far away f and g are, and we multiply it with pi. So this pi is a separate function. This pi x of z is a measure of how far away this given point, the perturbed points are. So z are the perturbed points. So we calculate the f of z minus g of c square, and we multiply each of those by pi and then do a summation. So we are doing the summation over all the perturbed points, right? And let's look at the form of this function pi. Pi is exponent minus d of x comma z the whole square divided by sigma square. Don't worry if you are not able to again visualize this exponent. The basic intuition behind pi is that the weightage of points that are really far away from the instance should be less. So the value of pi should be lower when the point is much far away from the original instance. So these black points should not contribute much to this loss function. The loss function should be mostly determined by the points that are in the vicinity of the instance. So how do we do that? We do that by defining this pi such that the value of pi decreases as the points move away far away from the instance. So now the loss function will take all of these things into account. It takes into account the distance between these points and the original instance, and also the distance between the simple surrogate model and the complex model prediction. Fine. Now, now let's look at the entire loss function once again. We have two loss terms, L, which we saw before, and the complexity measure of G, omega. I don't want to go into the details of the mathematical representation of omega, although I have shown it here. It uses a sparse linear model, but the details of this is something that for all practical purposes of actually learning to implement Lime, you can choose to ignore for the moment. Like if you are really interested, of course, you can read the paper and try to understand. But for the purpose of this lecture, I'm not going into the details of mathematical implementation of omega function. But basically, this measures the complexity of G. You want to minimize the complexity of G. This measures the kind of the distance, or you want to minimize the distance between the simple model and the complex model, complex global model and the simple local model. So that is the function L. And the summation of these two things is what you are trying to optimize, this function zeta of x. Okay. So this explains the mathematical implementation of the framework of Lime. I think you may still be not fully clear about the exact mathematical details of L and omega. And if you feel that way, it's totally fine, because when we explain how you implement Lime using Python, these things are not things that are going to be the bottleneck. The bottleneck is going to be your knowledge on how these things are codified into libraries and how to use those libraries and how to write the code in the first place. So we'll be more focusing on applied Lime rather than going into the deep theoretical aspects of it. But I think it's good for you to have an intuition about how mathematically this Lime is implemented, and this is how it is done. Okay, now before going into the details of how to actually implement Lime for a particular problem, let's also look at what are some limitations of this approach. There are several limitations to the Lime approach. It's not the best possible approaches for implementing explainable AI. It has a lot of amazing benefits like agnosticity. It's agnostic to the kind of model, so you can use Lime for pretty much any model. The intuition behind Lime is very good. Like, you perturb an instance and create data points and see how sensitive those perturbations are to different features, and that's how you know locally these are the features that are relevant. And if those features are not interpretable by human, you convert that into an interpretable format. It's a very, very simple intuition conceptually, but the issue is that when we are creating this perturbation in a local vicinity, how do we define the local vicinity? How do we define this? For example, how do we define this sigma? This is a measure of the size of this kernel. And how do we really define that? It's not easy to figure out what is the ideal size of the vicinity of the instance. So if you have an instance here versus here versus here versus here, if the model is really complex, so here the model is like not at all linear, it's very, very difficult to define the vicinity. So you may not get a comprehensive insight into the model's overall behavior from these localized linear interpretations which Lime provides. The second issue is again the core linear assumption that the Lime takes. Linear assumption is fine as long as as long as, let's say, within this region of interest around the instance if the model itself, if a global model itself is linear. But in this particular example that we have drawn, you can see that the global model is going non-linearly like this. Inside this region of interest, it's not at all linear, but we are trying to approximate the model using a linear function. So this is actually not good, right? You yourself can see that. And imagine if the model is even more complex and completely non-linear. The global model, when I say global model, I mean this function. If it is completely non-linear, it's very, very difficult to even locally interpret or locally approximate the model linearly, because how do you define that locality? It's very difficult to do that. So this assumption itself is a limitation of LIME. The second thing is stability and consistency of the interpretations that LIME can provide, because we are creating these perturbations around the instance a bit randomly, right? So depending on how these random samples are generated, we may end up getting different explanations for the exact same input. So let's say our point of interest is somewhere here in both cases. And let's say for whatever reason, the random sampling generated perturbations which are more in this direction. Now, what the interpretation here would be is that along the y direction, you have to, if you change the model, if you change the data along the y direction, there is a change in the prediction made by the model over here. Whereas if you change something in the x direction, there is not much change. And that's mainly because the boundary is almost like horizontal, whereas these points are almost vertical. But if you had, let's say, an evenly distributed random perturbations generated, this problem would not have occurred. Similarly, let's say the randomly generated samples are like this. Then when you try to, when you try to calculate the local linear fit, it will not probably approximate the global model really, really well. So the linear fit is heavily dependent on these random points, these random perturbations that are generated. So for the exact same input, meaning for the exact same instance which was here, if we are trying to interpret it, the interpretability is dependent on the random sampling. And this is a big limitation of LIME. And finally, the sampling itself, there could be bias in the way in which the LIME is generating these data points. Maybe, let's say the maximum blood pressure a human can have is 220. I don't know, I'm just making up a number. And let's say when you perturb, let's say a patient of interest or the instance, that person has BMI of 40 and blood pressure of 220, something like that. So in some extreme, and let's say we are perturbing that particular instance, then what happens is LIME might produce data points which are not real. Let's say LIME produces a blood pressure value like 300. Maybe 300 is an unrealistically high blood pressure value for a human being, right? But LIME has the potential to create such biased or even unrealistic synthetic data, which does not correlate with the kind of data you obtain from real life or real world. So that's again a limitation of LIME. But despite all of this, LIME still remains as one of the best methods for making your black box models interpretable. And it can be, if you know the details of how to make it extremely beneficial for you, you can apply it for tabular data, text data, and image kind of data. So we'll also be sharing the resources we use for creating this particular lecture. Let me just summarize the limitations once before that. So local versus global interpretability. The local behavior may not give any insight into the global behavior of the overall model. Linear assumption is a kind of a downside of LIME, because linear assumption may not be accurate, because the complex model itself can be highly nonlinear even within a small region. The points, stability and consistency is an issue. The random sampling that are generated can create inconsistent interpretations for the same data point. And finally, sampling bias. Lime can generate data points that are not corresponding with the actual real life data. So these are some issues with the Lime. And these are the references that we used for creating this lecture. So we refer to the paper, the original Lime paper. So we highly encourage you to have a look at this. And the GitHub repo is also cited here. We'll post the link in the description. And these 2 blog articles are also really good articles you can refer to for understanding the implementation of Lime and an intuition behind Lime. So hopefully this gives you a great idea about Lime, and we'll be covering the implementation of Lime using code in a separate lecture.